let me begin by asking people if they have any questions so far. No? All right. So I thought yesterday that I would take a break from hydrodynamics and do ADS-CFT, but I decided that since I sort of set you guys up, yeah. I have a bad habit of forgetting terms involving charges because I tend to just do things without charges. So there's a term involving the gradient of the chemical potential, because you have to write every vector and there's a gradient of the chemical potential. So instead of, but I'll postpone the ADS-CFT bit to tomorrow and instead talk about some more structural aspects of hydrodynamics. So the goal today, we'll see how far we get, is to try to show you that the set of axioms I gave you yesterday has a solution, has a classifiable solution that we can put down and say, okay, this is it, we've solved hydrodynamics. And when I say we've solved hydrodynamics, I insist that we've solved the structural part of hydrodynamics, all the structures that can show up that are admissible solutions to the set of axioms are taken care of. What we can't do is tell you what the actual physical properties of a fluid are. That requires understanding what the microscopic theory is. All right. So let's recall what we had yesterday. So we had conserved charges, which were functionals of conserved up to work terms and anomalies. And they admitted a gradient expansion. But were subject to this constraint that there was some other object, slightly less obvious one, the entropy current, whose divergence was required to be non-negative. And the way I formulated it and the way it's usually done is to require this to be true on shell. So when I gave you the exercise, I told you to eliminate the use the lower order equation of motion and then figure out what the constraints are. So the goal today is to sort of see, is very simple. So if this constraint wasn't there, as I said yesterday, we can do representation theory. We could just write down tensors willy-nilly as functions of gradients of these objects and we'd be done. And we don't have anything else to say because everything else requires microscopics. So I want to incorporate this constraint into the game such that we can basically go back to doing representation theory. Okay, so that's the goal. And to do that, I'm going to do some small manipulations. Let me introduce some new variables. So far this is just going to be a rewriting. The velocity field was normalized, okay, and if you don't have, for a moment if you forget about charges, then I just have a velocity field and a temperature, normalized d vector and a scalar. Since I have a normalized d vector and a scalar, I can always trade them for an unnormalized D vector by absorbing the scalar into the normalization. So let me introduce a new object. I'll call that beta mu, which is just the velocity field divided by temperature. The notation is sort of suggestive. It's going to sort of correspond to some kind of thermal direction, but not only keeping track of the thermal direction, but also keeping track of the size of the thermal circle using the inverse temperature. And so I'll trade the chemical potential for some other scalar quantity lambda beta, which is just mu over temperature with roughly speaking the temporal component of the source gauge field removed. Okay. So beta is like the velocity, so it's always, it's time lag, so it's pointing a long time. All right, so and then if I get lazy, I'll use another symbol to write down everything. The collection of all the fields for a charged fluid with one conserved charge, and I'm being reasonably agnostic whether this chemical potential corresponds to an abelian charge or a non-abelian current. It can be whatever, it can be, this guy can have some values in a Cartan of some Lie algebra, I don't care, but suppressing all the indices, I'm going to call this collection capital psi. This is just the collection of all the hydrodynamic fields. Two of them, beta and lambda beta, are the physical ones. They are the macroscopic fields that describe hydrodynamics, and G mu nu and A mu are classical sources. This is just relabeling of various pieces of data. So what we are after is, we are after T mu nu of psi, J mu of psi, an entropy current of psi subject to these equations. I'll write these equations generally, but I'll still be reasonably mysterious about what the anomaly terms are till we get to them later. Okay. So this is dynamics. And the constraint is okay. All right. So the constraint is subject to this dynamical equation, so I'm going to say it's on shell, but there's a very simple trick, a very simple linear algebra trick I can do, and I'll convince you that there's a very easy way to take this constraint off shell, which will be very useful in what follows. Okay? So let me do the following. I have some constraint. I can always add to any constraint the equations of motion with some Lagrange multipliers. Okay. So let me call this equation Let me call the left hand sides E mu and Ej. Okay. So Ej and E mu equals 0, Et mu equals 0 are the dynamical equations. So I can always do the following. I can pick a set of Lagrange multipliers which I have left mysterious for now, a scalar Lagrange multiplier for the current conservation equation, and a vector's worth of Lagrange multipliers for the energy conservation equation, and take linear combinations of them with the entropy current and demand that that combination be positive. So there's a very simple linear algebra theorem you can prove that. So clearly if this is true of shell, then when I go on shell, it's certainly true that entropy current remains positive, because on shell Ej and Et mu are 0, because on shell equations are just asserting that these two things are 0. Okay. Now this you can also prove that that once you allow yourself to, if something is true on shell, then it's equivalent to demanding that the correct off shell statement is this, with some set of Lagrange multipliers that need to be determined. It's very easy to prove in, say, if you have a finite system of equations that this is true. I'm just going to assert that this is true for continuum systems. But the question really is, what are these Lagrange multipliers? They're sort of mysterious objects. Okay, so we don't have much control on this so far. But recall that we have some field redefinition freedom. Whereby I had a velocity field, but the velocity field was not canonically defined, and neither was the temperature nor the chemical potential. So I can always orient my system, I can always choose, instead of making a choice like I did yesterday of the Landau frame or some other frame choice, we can always choose, we can fix this freedom by picking the scalar Lagrange multiplier and the vector and the scalar Lagrange multipliers to be the obvious dynamical scalar and vector data in the problem. The dynamical fields are a vector field beta and a scalar field lambda beta, but I'm going to pick the combination which gives me back the chemical potential is for hash. So the claim I'm making is that there's a canonical choice you can make of fixing yourself the Lagrange multipliers in terms of the physical fields, so that this equation which I sort of conjured up for you can be written completely in terms of the physical data No, I'm forgetting about Landau frame. I'm forgetting about everything. I'm basically saying that there's a way to align. There's a canonical alignment I can do. I have to fix Lagrange multiply somehow, but I can absorb that ambiguity by picking them to be aligned with the physical fields. Yeah, so usually you would have said no, but I'm saying that there's enough freedom in the problem, and there are other ways to motivate this, which I won't go into right now, but we can talk about it later. That this is the canonical choice, and we'll see that it ends up giving us everything we know consistent. So at this point, I can just tell you that this is the equation which encapsulates the constraints of the second law, but has a nice advantage of not having to solve the equation of motion because it's completely off shell. Okay. So let me do one small variant here. Let me call this combination delta, and the statement really is that this delta is positive definite. So this equation, I'm going to give it a name because it's going to be the sort of the key player for the classification program. I'm going to call it the adiabaticity equation. Yes?
So somehow it's like the time-like component of this curly epsilon mu, spatial component of this curly epsilon mu doesn't matter.
Well, you'll see in a second when I tell you the answer. You know that equation. It's just that it's not written in a form that's familiar to you. But yes, but it will capture everything. But the point is that, I mean, okay. What is true is the following: that if you are sort of in equilibrium, beta is really pointing along the time direction, and then it's completely true that the spatial components don't matter. Okay. If you're off equilibrium, beta has some spatial directions, so it's some admixture of things that shows up in this equation. Okay, and the equilibrium version of the statement, which if I don't write currents here and the gradients of currents, this formally looks like which you all recognize as the Clausius statement in thermodynamics. So this is like an upgrade of the Clausius statement to local currents in hydrodynamics. One that we are going to demand is true for every off-shell configuration. The demand that it's positive is a consequence of this.
But I can always switch the sign of, say, for example, mu, right?
You can.
So for any field flow, you're saying for any mu, it's always true.
Yes, I'm actually saying it much more strongly. I'm saying it's true off-shell. Yes.
So I mean, is it you are demanding or you can show it? Sorry.
My claim is that going from here with this data to here is an argument you can run through in linear algebra and show that this is true. This was always an axiom. This I have no idea where it came from. Let's say we have some intuition. We don't have a first principles derivation of this statement. But given this statement is given these three set of statements, this statement is true. No. Which equation? They can, yes.
Suppose it is just positive. That means mu is just positive.
Yes.
So if I have not chosen this particular Lagrange multiplier,
yeah,
I can as well make that field just negative.
No. So the claim is that there exist choices of Lagrange multipliers for which this doesn't happen, and but there's an anchor point for you in hydrodynamics, because in equilibrium no entropy is produced. Okay, so you can go to equilibrium, and if you don't like my argument about fixing these Lagrange multipliers there, you can go to equilibrium and use equilibrium to fix these values. So you see you have more physical input into how to choose the Lagrange multiplier than what I said, because there's equilibrium and the fact that there's some physical set of principles. So at the end of the day, there are many arguments you can give, but the mathematical claim I'm trying to make is that it's sufficient to study this equation, that everything you ever wanted to know about hydrodynamics is contained in that equation.
The right hand side implies the left, that I can understand.
Yes. So we are asserting that we are asserting this, yes. But I'll go through it with you later if you want to sort of see more details. Yeah. All right. So I should make some comments here. So this equation was not invented by us. This was invented by Loganayagam for a slightly different problem. He was interested in studying how these anomaly terms contribute to transport, and he motivated this equation. But the argument I'm giving here is a modern variant of that argument, which says that the structures of hydrodynamics are all captured by this one adiabaticity equation. So the classification program is simply this. We want to classify allowed constitutive relations by finding all solutions to this equation, which I won't write out in explicitly. And let me tell you the answer. And then tell you how we got the answer. There are precisely 8 classes of allowed hydroconstitutive relations. Yeah. Sorry? It is strictly less. I think my understanding is that it's exactly the same. Why is it less? So right now I'm just going to I'm not going to tell you the dynamics I'll have to put in later. Yeah, so I'm just going to ask what are the allowed constitutive relations. I'm not going to, as I said, I don't want to solve equations of motion. So if you like really what I'm after, at the end of the day, it's some completely off-shelf formulation where I don't ever have to keep solving hydro equations order by order to tell me what I can do at later higher orders. So suppose someone wanted to hand you a Lagrangian density, which gave you all the constitutive relations. They won't have to tell. They would tell you, okay, fine, just vary the Lagrangian. So later I'll show you a simple example where I can get dynamics, where this equation will sort of pop out. So in that sense, you're right. This equation will pop out in a certain class of examples of certain of these 8 classes as some kind of Bianchi identity. So it will just hold irrespective of what the physical configurations are. But then I have to also give you a variational principle to give you dynamics. So I'll show you how that works. Yeah, in that sense you're right. But I mean, for me, the motivation is roughly speaking something like this, that D stands for dissipation, and these are easy to remember. The H stands for hydro, and the bar or unbarred, the bar, no bar refers to hydrostatics, that is equilibrium, and bar refers to hydrodynamics, that is non-equilibrium. So, and S stands for scalars, and the V stands for vectors. There are, of these 8 classes, that's the only thing that causes entropy production. Dissipation is the only source of entropy production. This is the only thing that sources delta. The remaining 7 classes don't source delta, by which I mean that this combination identically vanishes in the remaining 7 classes. Okay. Off shell. The remaining classes have an action. The surprise, the bigger surprise to me, is that only these 2 classes have a normal action. The remaining 5, for which you would have said have a normal action, they don't without doubling, and something else which I'll tell you later. Without some kind of doubling, which so if you haven't heard about what this means, wait for it. I'll explain what that means. Off shell. At this point, I'm being completely agnostic of equations of motion. So forget that you ever heard of equations of motion. We're just going to solve this equation as one set of constraints on 3 currents. And the statement is that one equation on these 3 currents has classification in terms of these 8 classes, and this is what there is. So I mean, I wasn't going to do it in this order, but let me jump ahead and tell you an answer, just to give you a feeling. So let's talk about class C. Here's a constitutive relation. Forget about energy, forget about charges, peak sum, conserved, vector current, and call it your entropy current. Okay. Sounds silly, but such currents exist. In topological sectors. So you have some ground state degeneracy even in a thermal system for which there is a conserved entropy current. So Zohar yesterday mentioned the Pontryagin class in ADS4. You could, for example, forget about the Pontryagin class and take the Euler class or just the Gauss-Bonnet term in ADS4. The Gauss-Bonnet term is a total derivative, but it contributes to black hole entropy and therefore contributes by AdS-CFT to fluid dynamical entropy, but it doesn't produce energy, it doesn't produce charge. So it's an example of a exactly conserved current that does the job. But here delta is clearly 0 because this combination is clearly 0. So that's a trivial example of a class of configurations. Not every other classes won't be so simple, they will be a bit more complicated, but we'll get there. Huh? Can I write the current? Yes, I can, but let me make that offline. As I was describing to you yesterday, ABJM on at finite temperature has contributions from bulk Gauss-Bonnet term. Whether this this is by itself. This is not. Yeah. So I think it's not the most interesting class, but. But I was off shell, right? So this is this is a piece of the constitutive relation. So let me be a bit more clear. So I have a full T mu nu. Okay, it's just a piece. Yeah. So I'm just going to break up my T mu nu into 8 classes, and I'm just going to tell you what the answer is for each class. So in this class, it looks like this. That's all. So the full T mu nu is a linear combination of answers for 8 classes. Psi was what I just erased here. It's the combination of the fields beta mu, lambda beta, g mu nu, and a mu. And no, they are just fields. So think of psi as like the collection of all the fields that are physical fields for which hydrodynamics has to be described in terms of. I'm just saying that these guys are functionals of those fields. Yeah, I'm just saying the functional form is given by this. So this just asserts that pick any functional form of J mu, which is identically conserved, J mu s, and then you're in business. That defines a class. Okay, so don't worry if this still seems very abstract. I'm going to finish. By the time I'm done, you will see what all the 8 classes look like. I'm assuming that whatever is true. Okay, so the assumptions are whatever is true in thermodynamics are true. Okay, but they will sort of follow in a second if I tell you what hydrostatics means. So I don't have to assume it, but yeah. But at this point, you can say, look, you can take the following philosophy, and this philosophy is useful. As I was saying moments ago, as a low energy theory, hydrodynamics to me is a mysterious theory, because you don't write down an effective action and say, here we go. These are all the terms allowed in an effective action. You write down some set of currents and then you do some manipulation. So, in some old-fashioned language, you might want to call it a current algebra. It's not strictly speaking a current algebra, but it's an algebra on currents.
Is it possible for the entity current to be conserved? Grad mu, J mu, S equals 0.
Yeah.
But E mu and J mu not to be equal to 0.
Okay. In other, there are other classes where a version of that statement will be true. Yeah. For example, in class B, there will be no entropy production. So when I say that delta E equals 0, okay, maybe I should be a bit more clear here. Delta equals 0 means, strictly speaking, on shell there is 0 entropy production. Okay, so these are cases where J mu s, strictly speaking, is not so exciting because entropy is not produced.
No, all I'm saying is that here delta is the sum of 3 terms.
Yeah.
In this class, each of those 3 terms are individual.
Yes.
But you could have just the first term be 0 and the other.
So we'll have things like that. Yeah. So those will be sort of simple examples of how things work. So let me do one small manipulation before I proceed to give you the other classes. And the small manipulation involves one more unfortunate redefinition. The whole program looks very nice once you relabel things into different fields. But these are the sort of canonical variables that everybody likes to use. But the answers are less transparent in these variables, though we can work with them. So let me introduce one more object and tell you why I want to do this. So I talked about energy current, I talked about charge current, I talked about entropy current. But I also motivated my discussion yesterday by saying that I want to be in a Gibbs ensemble. Entropy current is not a natural object in a Gibbs ensemble. There's a more natural is a free energy current. Okay. So let me just do the Legendre transform I would do from going from the microcanonical to the Gibbs ensemble to write down a free energy current and introduce a J sigma, which is just this object. Okay, so beta mu is like 1 over T. This is energy, this is chemical potential, this is charge. This is like S plus E over T plus mu over T Q, which is free energy up to a minus sign. I've put that minus sign there. In some formulations, in some piece of literature, this part is called the canonical piece of the entropy current. The combination, which is energy momentum times velocity plus charge times chemical potential, is called the canonical entropy current. And so the piece of the entropy current that's not canonical is captured in the free energy current. Very good. Oh, this is minus Js canonical, whatever. All right, so there's a little bit of linear algebra. You can just plug in this guy and let me write for you what this looks like. So of course d mu of j mu s becomes a gradient of the free energy current. The anomaly pieces combine, I've just combined them into some form. You can work out what this is. But there's something nice that happens. The right hand side simplifies enormously. I haven't told you what these variations are, but what you get is the stress energy tensor contracted with some variation of the background metric, and the charge current contracted with the variation of the background gauge field, and delta B stands for a DFIO plus flavor gauge transformation along the vector beta mu and scalar lambda gauge parameter lambda beta. Okay. We know what the form of diffeos is. So if I have a vector, so delta B on G mu nu. So if I am trying to do a diffeo, only thing I care about is this vector part. Beta is some vector. It's a physical field, but it's a vector field in space time. So I can of course lead drag. I can do a diffeo along that vector field. I can change coordinates by changing physical coordinates to be transformed along that vector field, and the diffeomorphism that I do acts as a lead drag along this vector field, which of course you can always write as a covariant derivative of this vector with respect to the background metric. Okay. So that's the definition of delta beta, delta B of G mu nu, and delta B of A mu is a gauge transformation which takes the form is a gauge covariant derivative of lambda beta plus beta A t, or beta A, no t. It's very important that when I do a gauge transformation, I do a gauge transformation along lambda beta, but the diffeo also acts on the gauge transformation, and that piece gives you this. Okay. Because it's a vector, it also transforms non-trivially under diffeo. So basically it's like the usual gauge transformation plus lead drag of A mu along beta, which I've simplified here. Okay, so if you really want, this is really, it's L beta of A mu plus commutator terms. Gradient of lambda beta. Okay. Yes. How did it become an equality? Because you see, I have an equation here. I dropped this last part, so this whole thing. So the thing that really needs to be bigger than 0 is delta. Yeah. I defined this combination to be delta, and the combination was supposed to be positive. So delta is supposed to be positive, right? So I can write, this is just a defining equation for delta. So it's a defining equation for delta that I've written out here. Yeah. So all you have to make sure is that this combination ensures the delta is positive. That's all. So of course I can pull everything to the other side, but there's a reason to do it this way. But yeah. So far so good. Yes. Yeah, it's what you should think. So the anomalous contribution to the energy momentum tensor and the anomalous contribution to the charge current are easy to define. So when you do the Legendre transform, there is an anomalous contribution to the free energy current. So it's whatever is left to make that. So what I had a perpendicular sign in the first equation, they basically combine to give you this thing. Okay. So let's now try to yeah, I was assuming that it was. I mean, I could simplify my life and keep it abelian. So if it's non-abelian, then basically what happens is, if you have a non-abelian flavor transformation, at every local domain where the fluid is in local equilibrium, you can diagonalize to you can go to the Cartan basis, and you can assign chemical potentials along the carton. But as you go from domain to domain, you can rotate the carton. So mu takes values appropriately. So everything has to be gauge covariantized. So I mean, okay, the only reason to do all this is that the case where they really show up is here. So if you there's some non-trivial checks you can do if you have non-abelian flavor, which you miss out if you just study abelian flavor. In fact, so for many purposes, for testing various computations, it's useful to keep this non-abelian, because when you do the flavor transformations, life becomes very clean. The anomalies are very constraining. So you find yourself quickly getting into sort of highly constrained situations when doing manipulations, because certain things will not be allowed, and that's why it's useful. But what I'm going to do immediately, which was my next statement, is in the interest of time, I'm going to tell you that there's a story for anomalies. There's a very nice story for anomalies, but I'm not going to talk about the story for anomalies and tell you that this thing can be dealt with. We can talk about it in private, or we can discuss it at some other time, but there's just far too much notation and baggage to sort of work through what happens there, and the remaining class is a lot more interesting. So let's just take my word that anomalies can be dealt with. So then I'm going to sort of find for you solutions to the remaining 7 classes, okay? One of which I've already shown you, and I'm going to tell you how things look like. That's correct. This is correct. This is indeed correct. Okay? All right. So, yeah.
About the class C.
Yeah.
I mean, what do you mean by J mu? There's no term in J mu, but you have a term in J mu S. That's what you said. But I don't follow. Why do you call it as a transport coefficient? Or
I didn't say it was a transport coefficient.
So it's just one allowed term in J mu S, right?
That's right. So my set of constitutive relations, I've allowed myself to be off shell, and as long as they can give you a set of conserved currents, for the physical set of conserved currents as functionals of fluid fields, and an entropy current functional of fluid fields, I'll declare victory, satisfying that equation. Here was one. You may rightly say it's very boring. I will not disagree with that, but it's a solution. Formally, it's a solution to the set of equations.
But I could have added the same term in the J mu, right? That would classify to some other term?
That's right. That will go somewhere else. But yeah, so there will be other obviously conserved currents, but yeah, this could be physical. All right. So now let's use this equation. I'll use the equation in terms of the free energy current, so, and I'll drop the perp term. So it's basically just this. There's a gradient of some vector, which is contraction of energy momentum tensor with lead drag of metric, contraction of charge current with lead drag of gauge field, and this delta. Okay. I'm this guy, right? Yeah. So what I'm saying is that guy belongs to this class A. Okay. So it's part of class A. Class A, I at least for now I'll postpone. So if you really want to know what class A is, I can talk about it tomorrow. But let's say it can be dealt with. So if once class A is dealt with, the perp goes away. Okay, so let's do class B. Here's the solution. Staring at us in our face because I can set delta to 0. This is contraction of a symmetric tensor with a symmetric tensor, but I can make that symmetric tensor by contracting an anti-symmetrized 4 tensor with a symmetric tensor. So n is a 4 index object which is symmetric in its first 2 and second 2 pairs of indices, and 2 of its indices are soaked up by delta Bg. So when I contract this with this, I get 0. It's a bit easier here. I have an antisymmetric 2 tensor dotted with a vector. When I dot it back with the same vector, I get 0. And okay, you can generalize a bit, which is in the paper. You can also add here a term involving delta Ba and compensate for it here by adding a term involving delta Bg. So there's a bit more general solution, but this is the general structure. But you see, there's something nice here, and it explains the terminology. S is like an antisymmetric 2 tensor. Sorry? Yes? No, it's n alpha.
Next one. It's a minor point.
Oh, sorry, this is alpha. Yeah. See, S is an antisymmetric object. It looks like a field strength in physical in some configuration space. And 2 minutes of thought will tell you that n is like a Riemann tensor. Hence, it's like a curvature term in configuration space. And curvature terms in configuration space, you get typically when you have Berry phases. Hence the name. Which Bianchi identity? This is just an analogy. There's no. We don't derive it from. In some cases, they do. For some classes of transport, we don't know if they do in general. It's just a. They do. I mean, the precise word we gave was very like terms in the paper. So. No. Zohar was worried about something else. He's right that I have no right to call this curvature. No. This is just some random tensor. Any random tensor will do the job. That's a separate problem. I wasn't interested in solving it. See, this is an acceptable fluid configuration. So then you have to solve the fluid equations. It's an accept. So this class of constitutive relations can arise in some fluid. Okay, whether it arises or not depends on microscopics, and the transport coefficients are buried in n. Maybe I should give you an example of this guy. Let me see if I remember. Okay, so one example is Hall viscosity in 2+1D parity odd fluids. Where T mu nu looks like if you have parity odd, you have an epsilon symbol in 3 dimensions, and you can use the epsilon symbol to contract the shear tensor and a velocity field. It's a one derivative object. It shows up at one derivative level in parity odd fluids. Hallmark of this is that it doesn't produce entropy because delta is 0. You can have a flow along this guy and it doesn't produce entropy. Good? Good.
For arbitrary n and x, how do you know that delta is 0?
Because I don't, oh sorry. There is no free energy current. The solution to the adiabaticity equation is one where there is no free energy current. These guys take this form and delta is 0. So in this case you have an entropy current, but it's just a canonical entropy current, yeah, because it's the entropy current that you get by solving this equation for J equals 0, G equals 0. Sorry? This is just this is for a chargeless fluid. Yes, yes. There's another term, the Hall conductivity term, which will have a J. I just don't remember the tensor structures offhand, but we gave the answers in the paper. It's 10. How long can I go? 10 minutes, okay. All right, good, good, okay. So let me finish the first 4 letters of the alphabet and then leave the H's for later. Okay. So A I sort of fudged, B I told you, C I have also told you. Let's do D. The real insight here, which I'll explain in a slightly different language, which we found very useful, but the insight here was due to Shanthani, who basically convinced us that in a very nice series of papers, that if you can constrain the dissipative terms at the leading order in gradient expansion, then you don't care. So what do I mean? So let me simplify life and give you an answer. Give you a picture for neutral fluids. So consider what we said yesterday. Which is related to your exercise, but so my energy momentum tensor starts out its life as the perfect fluid, and then it has some shear terms and bulk viscosity terms. And the entropy current starts out its life as this guy plus corrections, which I insisted to you were vanishing yesterday. You can compute delta here because you can just evaluate expression now. I have a form for the energy everything. So delta turns out to be eta times sigma squared plus zeta times theta squared. So in this language it's very clear why eta and zeta have to be positive. It's just a statement that delta is positive, tells you that eta and zeta have to be positive, because this is a product of two symmetric matrices. That's manifest, theta squared is manifestly positive. So So done. But now if I go to higher orders, so if I go to one higher order, we will have new sets of terms. I will convince you momentarily what this, more formally what this set of terms will look like, but basically the logic is going to be that delta here starts out at second order in derivatives. It starts out as sigma squared and theta squared, each has two derivatives, and then there is some 3 derivative object and so on and so forth. But so for example delta 3 is some scalar built out of with 3 derivatives, okay, some scalar object built out of 3 derivatives, and you can quickly convince yourself that there are only so many choices. There is a theta cube term, there is a sigma 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 term, there is a theta sigma sigma term. Let me write it like this. This is just cross contraction to give a scalar. So okay, but something nice happens here. See, hydrodynamics is the gradient expansion. So 2 derivatives are always. Why they don't appear? So the entropy current. Your exercise was to show the coefficients in the entropy current was 0. Yeah. So they don't show up, but so I'm using that answer to simplify this. Okay, so good. So you can convince yourself. So I'll give you the formal argument in a second when I give you the full argument. But let's say that this is true. I'm going to go back to that equation up there and give you an argument along these lines that will immediately convince you that those things won't show up. But I just want to make one point here, which is more manifest if I just keep these terms. Since we are in the gradient expansion, 2 derivative objects are much bigger than 3 derivative objects. The only 3 derivative objects that are bigger than 2 derivative objects are if they are new 3 derivative objects that are not determined in terms of 2 derivative objects. In other words, theta cubed is parametrically smaller than theta squared, sigma cubed is parametrically smaller than sigma squared, and sigma squared theta is parametrically smaller than either of them. If you count gradients as 1 over temperature,
but
yeah.
Suppose I have transport coefficient in front of them. And
Yeah.
transport coefficient for the other is say order. Then how will I?
Well, but whatever there's some transport coefficient there's some coefficient here, right? There's some number here that combination of transport coefficients and terms of entropy current, doesn't matter. But our goal is to ask whether they can ever make whether this term in delta 3 can make delta negative. The answer is no, because whatever these guys are, if these guys are non-zero, then they always dominate over this. It's like saying you're doing Taylor expansion near the origin, and so I have a positive definite quadratic potential and have a small negative cubic term, but the negative cubic term is not going to modify the quadratic, is not going to destabilize the theory.
I would understand the coefficient is large, like at the order of 1 over theta.
No, that would why so but in every fluid flow, theta will be parametrically smaller. So I'm just saying that you have to irrespective of the coefficient, the gradient expansion is what matters. You're only supposed to deal with this momentum by momentum, and derivatives count more than coefficients. Okay, so coefficients here are completely unrestricted, and delta still remains positive definite. Dangerous things happen when either assuming that eta and zeta are non-zero, when you have something like a derivative of sigma. Okay, so pick something here. They will. So this combination, the coefficient here is coming from higher derivative terms in T mu nu and in J mu s.
But they can't come themselves.
They can. I'm just saying that those transport coefficients are unconstrained. They can have either sign. You can't say anything. The second law doesn't tell you anything useful about them, like it did for eta and zeta. So just to give you a feeling, there is a term here. Which is a two derivative object, which does actually contribute to this guy, but it doesn't make a difference. Lambda 1 is, you can't say anything about lambda 1. These terms are dangerous because it's a new gradient. In Taylor expansion, it's not something that's determined in terms of previous guys. Now Chantrey's result, which I will explain slightly differently tomorrow, is that you can always shift is that you can always shift the lower order terms and get rid of this dangerous guy. So basically you can write this as eta times sigma minus something whole squared and to absorb this gradient term. So you can always find, and the something has one extra derivative, so you push things to higher orders, but the statement is that you can recursively do this. Okay. So this argument is quite complex to see that this actually works, but I'll give you a very simple argument, a variant of that using the structures here, but I think, why is this dangerous term? Because you see, okay, good. So when I said that these terms are irrelevant, I'm using the fact that in every fluid flow, if there is a sigma squared term at second order, then I know that the sigma cube term at third order can't be bigger than that sigma squared term, right? Something like that. You can use those language, but I'm just going to say in the gradient expansion. But if you have this kind of term, you can imagine setting up locally a configuration where sigma is 0, but u dot grad sigma is not 0.